So far we have discussed about the mass transfer processes where we have the transfer of solute from one phase to another phase only, right. That means a solute, one or many, is having a unidirectional transfer from one phase to another phase. Just as an example, in absorption, we have this is the liquid phase, this is the vapor phase, and solute A is transferred from vapor phase to the liquid phase, but there is no transfer from liquid to vapor. So, this is absorption, right. So, if we additionally think that this is stripping, so here we have the stripping. Right. So, you see on the other hand, if it is humidification, here we have water, we have air, and the transfer is from this direction, the mass transfer we are talking about, right. In drying, this is the solid, this is the gas. The moisture is transferred from the solid phase to the gas phase. Okay? Now, the question is whether there is any other process where this transfer of species actually is bidirectional, right. That is, one species will be transferred from maybe liquid to gas, another species will be transferred from gas to the liquid, and that is basically the distillation. So, these are all one-way transfer, right, or one-directional transfer, or one-directional mass exchange. Now, if we think on the other hand distillation, you know what happens in distillation? In distillation, we actually have a contact between the vapor and the liquid phase, right. And the more volatile component actually moves to that vapor phase, and less volatile component which moves from vapor to the liquid phase, right. So, if I have liquid and vapor or gas, say A is more volatile, let us consider it is a binary system, A is more volatile and B is less volatile. Example, we can say that A is benzene, B is toluene, right. So, because the benzene has got a boiling point of 80 degree where toluene's boiling point is 110 degree. So, benzene will be transferred from the liquid phase to the vapor phase, right, A, whereas toluene will be transferred from the vapor phase to the liquid phase. So, this is a two-directional mass exchange which takes place in distillation, and that is why distillation process wise it is different, a bit different. We have in some different characteristics in distillation compared to absorption, stripping, humidification and drying, right. And what is that specific difference? The specific difference is that here we have two operating lines, we will see later that we have two multiple operating lines, okay. Whereas in absorption, conventional absorption, stripping, humidification and drying, we have only a single operating line. So, what is distillation? So, this is the speciality from the perspective of interfacial mass exchange or interface mass transfer, right. So, what is distillation basically? Distillation is a partial separation, right, based on the relative volatility of one compound or volatility of one compound, which may be higher or lower with respect to the other. Okay? So, it may not be a single compound, it may be a group of compound. So, there we will have a fractionation, we can get different multiple products, right, if it is a multi-component system. Generally, we have multiple product withdrawal. Okay? Like the typical example is the atmospheric distillation of petroleum, crude petroleum after desalination and heating, right. We feed that in atmospheric distillation unit, where we separate multiple components. From the top we will get a bit of methane and ethane, C1 and C2. Next we will get LPG, which is C3 and C4. Next it is the naphtha. Next it is the ATF and kerosene. After that we have the diesel, and finally the different reduced crude oil, which is the feedstock for the vacuum distillation unit, which is further fractionated into different lube oil feedstocks like intermediate oil, spindle oil, heavy oil, gas oil, etc. Right. So, that is the fractionation of a single mixture into multiple components, which are all basically these all products from a distillation column. They are actually multi-component mixture, but definitely the range actually is narrowing down. If in a crude petroleum we have the range of carbon chiral centers ranging from 1 to 70, that is from C1 compound to C70 compound nearly, right. So, we break it into multiple fractions based on our requirement. So, that is basically this distillation process. So, we simply apply the property of migration or exchange of more volatile or preferential tendency of a more volatile compound to go into that vapor phase, whereas the less volatile compounds tries to remain in the liquid phase. So, we can achieve a fractional or partial separation, because the vapor phase will be reached in more volatile compound with respect to the feed, whereas the liquid phase will be reached in the less volatile compound, right. So, the physical principle behind distillation is the vapor liquid equilibrium, which we have studied in thermodynamics, and again we will introduce some of the basic ideas here. We will brush up that ideas, right, whatever we have studied in vapor liquid equilibrium in process thermodynamics. So, we will do that. Now, you see that once we feed something, or we feed that mixture, the initial mixture, baseline mixture, to a device, right. So, if it is a single stage, singly for the just once it is achieving equilibrium between the vapor and the liquid. So, that will give you a kind of separation, right, which may not be meeting the desired requirement. So, in that case we go for multi-stage, just like any other mass exchangers, and we establish the counter current contacts between the liquid and the vapor stream. Liquid must be moving down, where vapor must move up, right, through this column. So, you see that in order to establish, if I have a column just like it is a plate column, typical plate column, we can use also in for other purposes, like for absorption we can use that, right, at least principally. So, we have the plates and we have the downcomers. This is another plate, this is downcomer, right, and there is the last plate. Here we have a seal and we have a partition here. Why, I will explain. So, we are delivering the feed somewhere here. There may be a feed preheater, and we have a feed valve which serves the purpose of a throttle valve, right. So, what will happen in say we consider after throttling we get liquid and vapor, right. So, liquid move downward and vapor moves upward. So, this is the vapor part of the feed, this is the liquid part of the feed, it moves downward. So obviously it will be accumulating here, and the vapor moves out, it's leaving from the top, right, vapor outlet. And if we have taking away the liquid, so definitely we are not establishing any countercurrent contact, right, because the vapor stream is moving up and liquid is moving down. Okay. So we are not generating any countercurrent contact over the trace. So what we have to do? We have to condense this vapor before final withdrawal, and instead of withdrawing it fully, we will actually redirect a part of the condensate again to that column in the form of liquid, and that can be accomplished if I have a condenser here, right, a condenser and an accumulator drum. So in the condenser we feed cooling water, right, and here the condensate accumulates. Now you see a part of that condensate we withdraw as distillate, and another part we pump it again in the form of liquid to the distillation column, right. And here we can adjust the ratio of this stream which we are feeding back to the distillation column by means of this valve. So this is basically called reflux. So reflux is a liquid, now it moves down, the vapor moves up, so we can establish a countercurrent contact between the liquid and the vapor stream, right. Now you may be thinking that why I have drawn the pump here to avoid the cumbersome figure. No, the pumps, this is called the reflux pump. Reflux pumps are always placed at a level which is much below this accumulator drum. So this is the condenser, this is accumulator drum, right, and this is the reflux pump. So you see this reflux is just saturated, maybe it is having 1 or 2 degree of subcooling, right. So if I feed a saturated liquid to a pump, what can happen? It will be leading to inevitable cavitation. So to avoid the cavitation, we know that cavitation can be avoided if instead of lift, we just go for a negative lift. This is the suction point. With respect to the suction point, the pump inlet is having a negative datum or negative elevation Z. So this is Z equal to 0, here Z is negative. So whenever Z is negative, actually it adds up to the NPSH, right. So we can avoid cavitation in the reflux pump, and that is why we place it at the bottom. Now you see that that's for this liquid, this part above and over this feed, portion of the column above and over that feed, and we have established a countercurrent contact. Now what will be for the countercurrent contact for the part below this feed inlet? See, we have the liquid accumulating here, right. So we will feed it to something which is called reboiler, right, a shell and tube type device where vaporization actually takes place, and we give a heating fluid, that is saturated steam, and we withdraw the condensate from here. So the vapor is fed back to that column. Right. So, the liquid moves downward and the vapor now moves upward here. Right? And we establish the countercurrent contact. Now, what about the withdrawal from here? See, from this partition, when the liquid overflows, here from we will withdraw the bottom product. Right? This is called bottom product. Now, if feed is a mixture of A and B, let us consider a binary distillation column. Right. If feed is a mixture of A and B, you will get a distillate rich in A, because A, according to our notation, is more volatile component. Right. And the bottom product, which will be rich in B, the less volatile component. So, you are getting a partial separation by means of this distillation column. So, there are two additional accessory which we require, right, in addition to the column, and that is condenser and the reboiler, which facilitates the countercurrent contact in the two portions of the column. The half of that column which is above and over the feed, it is known as rectification section, and the part which is below this feed, it is called the stripping section. Right. What is the idea? Why these two are named? Basically, you see that if I consider the part above and over that of feed inlet, what happens? That this part is closer to that vapor withdrawal, and vapor should be rich in A, right. So, here if I think of the desired mass exchange in this rectification section, we have to understand that this is the vapor stream, this is the liquid stream, the vapor is our focus, right. The vapor is basically the focus, okay. So, from the vapor, vapor should be enriched in A, okay. So, B should be transferred, whatever B is remaining should be transferred to that liquid phase. Simultaneously, there will be transfer of A, enrichment of vapor in terms of A. However, the primary objective is to release the B from the vapor phase, more and more B from the vapor phase, okay. So, that is why it is called rectification. Whereas, for the part below this feed, we have again the countercurrent contact. Here, the liquid is to be stripped of A. So, this is vapor, this is liquid. So, we must transfer more and more A, the more boiling component, from the liquid phase to the vapor phase, right. So, it is very similar to the stripping operation what we have studied initially, okay. So, that part is called stripping section, this part is rectification section, and this is the typical multi-stage continuous binary distillation column we have, okay. And the structure internally is very similar to the standard plate column. We have a partition here, and the partition why it is maintained, this liquid head is necessary for this head to be generated such that the liquid must flow through the tubes, right, and it should be vaporized and the vapor should be fed back. So, for this entire loop to sustain in terms of initial liquid and then finally vapor, we must maintain an initial pressure head, and that is being maintained because of this partition. So, whatever is the overflow from this partition into that other side is being withdrawn as a bottom product. Okay. So, that is the overall idea, very basic, very qualitative idea of distillation process. Now, once we have the basic idea of distillation process, we must know some of the industrial applications, and there are many, right. Like, what is the purpose here? The purpose may be the fractionation of a feed stream. We want to fractionate or break that feed stream or feed solution into different components. So, the objective or the purpose behind distillation, you see the first one is fractionation. So, you want to recover the different fractions, all are valuable from a feed stream. The typical example, number one is petroleum refining. Like feed is crude petroleum, so we feed that after desalination, salt removed, and then after heating we feed it to the distillation column, right, which operates in atmospheric pressure, and that is why it is called ADU, atmospheric distillation unit. From the top we get C1, C2, methane and ethane. From here C3, C4, that is LPG. Then we have naphtha, right. Naphtha is basically, there are two different cut. So, and this naphtha, which is a low cut naphtha, which ranges from C5 to boiling point around 91 degrees, something like that. So, that is the low naphtha, and there is another heavier molecular weight naphtha. After that we have this SKO, superior kerosene oil, ATF, aviation turbine fuel, MTO, mineral turpentine oil. Then this LSD and HSD, high speed diesel and low speed diesel, and finally the reduced crude oil, which is fed to vacuum distillation unit, right, VDU. So, from the top of the VDU, these are higher fractions, gas oil, then we get spindle oil, then we get intermediate oil, then the heavy oil, and final residue, which is fed to this coke producing, petroleum coke producing units and all, right. So, this is the petroleum refining's very basic overview, where the two major distillation column actually are the central equipment of this refining. Next is cryogenic distillation of air. Here also we get different fractions. So, air first it is to be cooled, right, and liquefied, and then what we will get? This nitrogen, oxygen and argon. These three are the major important gas streams we can actually generate from these cryogenic distillation units. So, that is basically the example of fractionation, right. The second is recovery of a product, right. So, recovery of a product, like example, number one is the separation of ethylene oxide and water. So, ethylene oxide in water, that is another example in relation to the recovery of a product. Ethylene oxide is definitely the product, right. When it is generated through reaction, it is getting, we first absorb it in water and then basically recover the ethylene oxide again from water. So, that is an example. Second example is ethanol water. So we do it in distillery to produce alcoholic beverages. So third example may be this styrene and ethyl benzene. Right, here styrene is the product which we recover from ethyl benzene. It may be propylene and propane. What we recover is propylene. And lastly, in addition to fractionation, recovery, and last is removing impurity. Right. Now, benzene, the impurity here is water. Now, benzene, before we fed for chlorination, we should remove this water. So, benzene plus water. This water is the impurity here, which we actually remove from this feed, right? Little amount of water is present, but that is to be removed because we have to go for chlorination, and in chlorination the presence of water is to be totally avoided. So, benzene is to be fractionated, benzene water mixture is to be fractionated to get nearly pure benzene. So, these are the main purpose. The first one is fractionation. I have given two examples. Then recovery of product, there are different examples, and finally removal of impurities. So, with that idea, let us now go for revisit to this thermodynamic equilibrium concept of vapor and liquid, right. So, we will study a bit of VLE, and after that we will try to understand the VLE problem. Basically, we have solved in thermodynamics, that is a flash vaporization, but in thermodynamics we have solved it for multi-component system. Here we will do it for a binary system, and we will try to understand the graphical implication of these equations. So, you see the vapor liquid equilibrium is basically the primary condition for this vapor liquid equilibrium is we have a vapor phase, we have a liquid phase, and here the components I are 1, 2, 3, here 1, 2, 3, right, and it has got a fixed temperature and pressure. The fugacity in this liquid phase is Fi cap L, component species fugacity. Here the component species fugacity is Fi cap V. So, at equilibrium, Fi cap V is equal to Fi cap L. Say Fi cap V is equal to phi I cap, component species fugacity, into Yi into P. So, Yi is a mole fraction in vapor phase, right, that we will use as a universal notation, that Y is represents the, here in distillation Y represents the composition in vapor phase, where Fi cap L is equal to gamma I Xi Fi naught, right. So, gamma I is the activity coefficient. X is the liquid phase mole fraction, and Fi naught is the standard state fugacity, right. Now, for simple solutions, as you all know, according to Lewis-Randall rule, Fi naught is equal to Fi. And which are simple solutions? where in pure form all the component species present in the solution exist in the same physical state as that of the solution at the same temperature and pressure, right. Like benzene toluene mixture is typically a simple solution, and say benzene toluene mixture at 1 atmosphere and 30 degrees Celsius, right. It is a simple solution. Say Fi cap is equal to Fi, and Fi we may have a high pressure in the liquid phase. We can write it as Phi I, or rather this Fi sat, saturation fugacity, into Pf, that is a pointing factor. So we have discussed it in thermodynamics. Basically, again we are doing a bit of brush up. So Fi sat is Phi I sat into Pi sat according to the definition into Pf, and Pf you know it's an exponential of this VIL P minus Pi sat by RT, right. So if I substitute it, I will get Phi I cap Yi into P is equal to gamma I Xi Phi I sat Pi sat into Pf. So further we cross multiply Phi I sat and we write this as Phi I into Yi into P is equal to gamma I Xi into Pi sat into Pf, where capital Phi I is basically Phi I cap by Phi I sat, right. So that's the general VLE. General vapor liquid equilibrium. Now, for low to moderate pressure, distillation we generally we carry on distillation process at low to moderate pressure. Low to moderate pressure means P less than 10 bar, because the separability increases at lower pressure, right. And that's why you see that whatever we cannot separate in atmospheric pressure, we have to go for vacuum, and the typical example is a vacuum distillation unit in petroleum refinery. So the low to moderate pressure, we have capital Phi I is close to 1, pointing factor is also close to 1. So we have Yi P is gamma I Xi Pi sat, right. So that's the modified Raoult's law. So here you see this is the fugacity of the vapor phase. So actually we have to understand the vapor phase we are considering is considered ideal. Right. The vapor phase is considered to be ideal, and that's why the fugacity is equal to the partial pressure. Whereas on the right hand side there is a liquid phase fugacity equivalent term, but that's not ideal because we have gamma. So that's the modified Raoult's law. Further, if we assume ideal liquid phase, then gamma I is equal to 1. So we have Yi into P is equal to Xi into Pi sat, and that's the Raoult's law, right. So that's the general vapor liquid equilibrium relation for a multi-component system. Now for a binary system, A and B, let Ya is the Y represents mole fraction in vapor, and X in liquid, X is that in liquid, then we can write YB is equal to 1 minus YA, XB is equal to 1 minus XA. Right. Now, we will actually drop the subscripts of A and B and we will write it plain and simple as X and Y, where X is basically XA and Y is basically YA. Right. So, let YA is equal to Y and YB, or sorry, XB or XA is equal to X. So, YB 1 minus Y and XB 1 minus X. So, we introduce the notation in terms of more volatile component. Right. So, you see YA into P is equal to XA into gamma A into PS hat. So, we define equilibrium constant Ka is defined as YA by XA, and that is gamma A into PS hat by P. So, similarly, Kb is equal to gamma B into Pb sat by P, and that's equal to YB by XB. Similar to the partition coefficient what we have introduced in liquid-liquid extraction. So, here K is the equilibrium constant. Right? Now, equilibrium constant will give you the relative enrichment of vapor phase compared to or with respect to that of liquid phase, right. So, YA by XA. So, definitely Ka we expect that it should be greater than 1, whereas Kb must be less than 1, because YB preferentially should be lower than XB and YA should be higher than XA. Okay? But that is not the quite a useful term, the equilibrium constant, but instead we use something called relative volatility, right, for detail or for better understanding. We introduce relative volatility, right, alpha AB. So, what is alpha AB? Alpha AB is YA by XA by definition divided by YB by XB. So, according to our new notation of X and Y, this is Y by X, this is 1 minus Y by 1 minus X, and from there we get Y is equal to alpha AB into X divided by 1 plus alpha AB minus 1 whole bracket into X. So, that is a typical equilibrium relation, right. And if I use this concept of K, so this is Ka by Kb, and which is more precisely gamma A into PS hat divided by gamma B into Pb sat. What is to be noted here, that this alpha for, see, let me discuss it. So, if I go by modified Raoult's law, so general VLE, right. So, this is according to the modified Raoult's law what we have used here. So, but general VLE Ka is equal to YA divided by XA, so which is gamma A, right, PS hat into PF divided by P into capital phi I. Right? Now you see that gamma, according to thermodynamic notation, is a function of this liquid phase composition. Capital phi I being containing in the numerator that phi I cap is a function of gas phase composition. So Ka is dependent on x bar means all xa, xb. Here definitely for this binary system, once we know x, we know xa and xb, right? Because xa is equal to x and xb equal to 1 minus x. So x by temperature and pressure, right? So on this, for this case, alpha AB, you see, so it will be, so this is phi A, right? So gamma A PS at by gamma B PB sat PF A, here A, divided by PF B into phi B by phi A. So this is also a function of temperature, pressure, liquid and vapor phase composition. Now modified Raoult's law, say if I have K, I know it is this, we have already proved it as gamma A into PS at by P. So K is a function of X, temperature and pressure, because P sat and gamma both are functions of temperature. So alpha AB is a function of, or is a function of X, temperature and pressure. Here alpha AB is a function of X, Y, temperature and pressure. Now for the Raoult's law, see Ka is equal to PS at by P, right? So Ka is a function of temperature and pressure only, whereas alpha AB is PS at by PB sat. Now you see, though PS sat and PB sat are strong functions of temperature, but their ratio is nearly constant, right? So it is nearly constant, or rather a weak function of temperature, right? So that's about the VLE, vapor liquid equilibrium. And you see that once we know, that's why in semester problems probably you have seen that alpha for a distillation, typical distillation problem, alpha is given as 2.3 or something, right? So why alpha is constant? The relative volatility, how come it is constant? It's constant because we are following basically the ideal cases of gas and liquid, that means Raoult's law. So you see that for distillation to be feasible, alpha AB must be much greater than 1, right? So then it will be techno-economically feasible, right? And the equilibrium data we can generate if we are provided with this alpha or we are provided with TXY data, like the TXY data, this curve we have seen that generally it is a length shaped region. This is T, this is X or Y, right, 0 and 1. So this is T versus Y, this is T versus X, this is liquid phase, this is liquid plus vapor, this is the vapor phase, and these are the structures of the tie lines which actually connects the equilibrium liquid to the equilibrium vapor composition. So if I want to generate this y versus x plot, we'll draw it like this. We'll draw a 45-degree line, right? And next, we'll take the projections of this equilibrium composition. Say this is y, for this tie line, this is x. So we'll reflect this, and on the 45-degree line, we will reflect this, so we'll get the point. So if we project this tie line data and join them, these points by a smooth line, I will get the equilibrium curve like this. So it will be kind of convex, right, for the typical vapor liquid equilibrium following Raoult's law, but it can be having a shape like this, or it may be like this, based on the non-ideality. The inflections, there are inflection points, right. So inflection may be present, it may be non-concave, non-convex type equilibrium curve if I have a higher degree of non-ideality, right. And you see that for azeotrope, what will happen? For a high boiling azeotrope, we know that I'm just discussing this high boiling azeotrope, which gives you alpha equal to 1. So it will be a kind of curve like this. Right? So if I project, I will see this sort of equilibrium curve. Why? Because this is t versus y, right? So if I draw a tie line like this, this is y, this is x. So this is x and this is y. So actually it will be like this. Like this. Okay. So for azeotropic composition, and this is the typical azeotropic compositions we have, where this y and x are same. And we have discussed for azeotrope, there is a low boiling azeotrope. And for azeotrope, according to modified Raoult's law, gamma A PS at is equal to gamma B PB sat. So that's all about the brush up regarding the VLE. So next we will go for flash distillation, which is a single stage continuous distillation process. So we will discuss about the flash distillation, which is a single stage continuous distillation process. So flash distillation, single stage continuous distillation process, right. So you see, we have the feed. Here we consider binary feed, F, ZF, right, where ZF is the mole fraction or mass fraction of component A. So that's the feed. First, it is to be heated. So this is the feed preheater. Next, it is to be flashed, means pressure reduction, and next there will be a separated drum. And separated drums, it's fitted with baffles such that we have enough contact time between the liquid and the vapor, and they attain equilibrium. The outgoing liquid and vapor stream in ideal condition we will consider that they attain equilibrium. So, this is vapor, the fraction, mole fraction or mass fraction of A is Y, and this is liquid, flow rate is L, and the mass fraction of A is X, right. So, it operates at a constant temperature and pressure, right. So, this is the flash valve and this is the separator drum or flash drum. Now, as we have discussed in thermodynamics, the overall material balance will give you that F is equal to V plus L. Component material balance will give you FZF is equal to V into Y plus L into X, right. Now, see the liquid to vapor, this fraction, right, amount of liquid produced and amount of vapor produced, we define Q as this, right, we define Q. Now, how to measure Q? Simply by enthalpy balance. So, enthalpy balance, so here F, here its specific enthalpy is HF. So, F into HF plus Q, whatever heat we are giving here, right. So, that is equal to L into HL plus V into HV. Okay. So, HF, its temperature is different. Now, L and V, that is HL and HV, we have to calculate from this temperature and pressure of the flash drum in addition to its composition, right. So, basically H here is a function of temperature, pressure and composition, and we know in thermodynamics how to calculate this function. Okay. So, there we have to use the different models, and from there we have to get the Gibbs energy for a mixture, right, and which requires this residual Gibbs energy calculation GIR, okay, or GR basically. GR is for mixture. Then we will take the derivative with respect to temperature, because we know that del del T of this NGR by RT is equal to minus of this HR by RT square. Okay. So, or NHR by RT square with a minus. So, from there we can calculate the residual enthalpy, and we know that absolute solutions or these ideal solutions enthalpy, and adding these two we can calculate the enthalpy of that solution, right, real solution. So, whatever it is, we will not go into that. So, if I divide this entire equation by F, so Q by F is equal to L by F, sorry, L by not V, it is L by F. So, L by F, that is Q, right. So, Q into HL, and definitely V is equal to F minus L. So, it is 1 minus Q into HV. So, we have this HF plus Q by F minus HV, this HV shifts it to this side, divided by HL minus HV is equal to Q. So, if I have a measure of these enthalpies, we can calculate the Q, right. So, Q if we calculate, here again we will divide it by Q, by F. So, this V is equal to 1 minus Q into Y plus Q into X. So, Y and X relationship we can obtain as Y is equal to minus Q divided by 1 minus Q into X plus ZF divided by 1 minus Q. This is called, and this is also valid, we will see later, that continuous distillation, multi-stage distillation column. This is called the equation of Q line or feed line, right? Because this is an equation which relates this y to x and feed composition, that is ZF. Now you see, if x we put at ZF, y, then y is also equal to ZF. So Q line must pass through the point ZF comma ZF, and its slope is minus Q divided by 1 minus Q, right? So its slope we are getting from the Q, and it is minus Q divided by 1 minus Q. Now how will you solve for this y and x, right? So you see that graphically we can do it, because this is one equation, this is another equation, and F and ZF, they are known. So you have to calculate VL and YX, correct? VL and YX, okay? So the thing is, if I can supply y and x, definitely we can solve for V and L. So V and L can be solved because there are two equations only and there are 4 unknowns. So what we can do, that y and x we can solve graphically by simply doing this. See, we'll draw this equilibrium curve. We'll draw this equilibrium curve, right? And here we will locate this 45-degree line. We will locate the point, so F, ZF comma ZF. And from this point, we will draw a line with a slope of minus Q divided by 1 minus Q. So where it intersects is basically X and Y, right? So how we can solve this? So solve equilibrium line equation, y is equal to alpha AB into x divided by 1 plus alpha AB minus 1 into x, and this y is equal to minus of q divided by 1 minus qx plus zf divided by 1 minus q. So these two equations, if I solve, I will get x and y, right? You don't have to go by graph, you can solve them analytically, and from there you can calculate this x and y knowing the value of q. Okay. So here alternatively we are doing that, actually we know the ratio of L and V, right? Because if I know F and we know the ratio of L and V, because L by F is Q, V by F is 1 minus Q, using this component material, this overall material balance and the definition, and from there we are extracting out the Q value from the enthalpy balance, right? If enthalpy is provided, you can solve for Q, and finally you can get this y and x, and that's all about the flash calculation. Okay. Now the point is that we can have the different slopes of the Q line based on the thermal state of the feed, and that we have to understand precisely. So that we have to understand. So first let's do the easy conditions. So Q lines for different thermal states of the feed, right? So first, it's a two-phase. So Q is less than 1 greater than 0 because some amount will be this liquid, some will be vapor, and Q is defined as L by F. So Q is between 0 and 1, right? So 1 minus Q is definitely negative. So slope, 1 minus Q is definitely positive. So the slope, which is equal to minus Q divided by 1 minus Q, will be definitely negative as we have drawn there, right? So let me enlarge this diagram. And this is the ZF, say this is X, this is Y, 1, 0, 0, 1, and this is the point ZF, ZF. From there we have drawn a Q line, and this is the typical condition for case 1, what we have considered as two-phase. So 1 means two-phase. Right. So next, it's saturated liquid. Right. Q is equal to 1 and the slope tends to infinity because the denominator becomes 0. So we have this for condition 2, saturated liquid. Right. Third is obviously saturated vapor. So Q is equal to 0 and slope becomes 0. So that's the third, saturated vapor. Now there are two other thermal states we have left. One is subcooled liquid and another is superheated vapor. Now think, if it is a subcooled liquid, when it is being fed to that flash drum, what will happen? F, and here it is V, here it is L, right? So the entire feed goes to the liquid, right, the entire F, but inside the flash drum or inside any distillation column, we have to consider all the streams to be saturated, right? So how we can convert to that hypothetically? This is hypothetical for the ease of calculation, not to perform the calculation. So what was the vapor flow rate originally? 0, right? So just to have a estimate of Q, we have to do that. So, but this is saturated. Sorry, this F is subcooled F. Okay. This is subcooled, right? So it is to be converted into saturation, state of saturation. How we can do that? We will think that though there is no vapor flow rate, from 0, some vapor will condense, right? Some vapor will condense, releasing the latent heat, which is just sufficient to increase the temperature of the feed from this subcooled state to the saturation state. We assume delta V amount of vapor will condense and the released latent heat will supply the released latent heat is just equal to the subcooled heat load of the feed. Right. So finally, this is saturated. So L is equal to F, the total feed will come to that liquid phase, plus the condensed vapor delta V, right? Now how much is delta V? Now how much is delta V? We have to understand that delta V into lambda is just equal to F into CPF Tsat minus Tf, right? That is the subcooled heat load. So L becomes F plus delta V, which is F CPF Tsat minus Tf by lambda. So Q, which is defined as L by F, is 1 plus CPF into Tsat minus Tf by lambda. So that's Q, and Q is greater than 1, right? So when Q is greater than 1, 1 minus Q is less than 0. That's negative, right? So slope, numerator is negative, denominator is also negative, the slope is positive. So we have this as state 4, which is subcooled liquid, right? And in the same way, we can solve for superheated vapor, where originally the liquid flow is 0 because the entire feed will go to the vapor phase. And we will apply the same strategy what we have used for the treatment of subcooled feed. So superheated vapor, here what we have, Q is less than 0 by simply the continuity of this progression of Q from one thermal state to another thermal state. But how it can be established? See, we have the same flash drum, we have F, that is superheated, so L is 0 and this is V, right? So entire F will go to the vapor phase, and additionally the liquid is 0, but just the reverse will happen, right? Some liquid will vaporize, right, taking up the latent heat from this superheated feed, and that will reduce this feed temperature to saturation. So delta L into lambda is equal to F CPF Tf minus Tsat, right? So delta L is equal to F CPF Tf minus Tsat, and obviously we have the V or L rather is equal to 0 minus delta L, so minus of F CPF Tf minus Tsat, because we have to calculate L, and Q, which is L by F defined as, it's equal to minus of CPF divided by lambda Tf minus Tsat, and that is negative. So if Q is negative, right, so slope will be positive. Why? Because the slope is minus Q, so minus Q will be positive because Q is negative, and denominator is 1 minus Q, that's also positive. So here also we will have a positive slope, but the line will be like this, okay? So this is state 5, that is superheated vapor, right? Now what you see, that even if it is superheated vapor, subcooled liquid, it's giving you a Y and X value. Like for subcooled liquid, this is Y, this is X, but there is no vapor phase. How come we are having a vapor composition? It's basically the infinitesimally small amount of vapor we consider, and if we have any vapor, then it will have a composition like this, and X will be actually ZF. So X and ZF, see X here according to our diagram, X is greater than ZF, right? But that's based on, that's basically due to the conversion of the thermal state from subcooled to the saturation. But actually, in reality, what we will get? We will get the entire, there is no separation, the whatever liquid we feed to the drum actually moving out as the same liquid, right? But for Q value calculation, so don't think that X and Y to be real, right? X and Y to be real, it has got no physical implications here, but for Q value calculation, which will be required for multi-stage separation processes, we should be able to draw these Q lines for different states of that feed. But in flash drum, you see that unless we have a two-phase, we don't have any separation. So this is basically the region, angular region, where we can have separation. If my Q line is outside this angular region, we cannot accomplish any separation, right? So that's about the flash calculation, and more importantly, the discussion regarding the Q line. So we'll have we'll continue this discussion of distillation in the next session, with starting with the typical batch distillation and the Raleigh's equation. Thank you.